Usually when you go to the garden center and you buy a bag of soil amendment, there's this expectation of a guaranteed benefit.
Right, yeah, you just expect it to work.
Exactly. You pick up a bag of something that's marketed as this, like miracle fertilizer, maybe it's a premium bag of biochar, and you sprinkle it around your prized tomato plants, and you just wait for the magic to happen.
You're expecting a massive harvest.
Right. You imagine you're giving your garden this ultimate high-tech, green thumb shortcut, but then, a few weeks later, you walk out to your yard, and your tomatoes haven't just failed to thrive, they are actively turning yellow.
Yeah, they look completely starved.
They do.
Nice.
And you're standing there holding this bag of expensive carbon-rich dirt, just wondering if you basically bought a bag of poison.
Yeah.
And if you're working in ag tech or environmental management, or even if you're just insanely curious about backyard chemistry, you need to know why this happens.
Oh, absolutely. I mean, it is the absolute definition of an agricultural paradox, and it happens to so many people.
Which is exactly why we're doing this deep dive today.
Yeah.
Our mission is to unpack a massive stack of recent peer-reviewed scientific reports. I mean, we are looking at stuff spanning 2023 all the way to 2026 to reveal the hidden, honestly intense chemical transformations that happen when organic matter gets baked into biochar.
Yeah, because the marketing hype around biochar has completely outpaced the underlying chemistry. To understand why those tomatoes turn yellow, we really have to look at the violent chemical transformations that happen to nitrogen and phosphorus during a process called pyrolysis.
Pyrolysis. Okay, let's unpack this. Right. Basically, that's when you take raw biomass, right?
Yeah.
So crop residues, animal manure, maybe municipal sewage sludge.
Yeah, any organic feedstock.
Right, and you trap it in a sealed oven. You heat it to extreme temperatures, but you completely starve the environment of oxygen.
Exactly, and that creates a fundamental tug of war. See, the extreme heat required to create that really stable carbon-sequestering biochar is inherently destructive, or at least highly transformative, to the very nutrients that crops need to survive.
Because there's no oxygen, right?
Right.
So it can't actually catch fire and burn down to white ash. The thermal energy just forces the molecules to rearrange.
Right, it bakes. And if we look at the fate of nitrogen inside that oven, it is wild.
Yeah, let's start with nitrogen, because raw feedstocks like dairy manure are just packed with organic nitrogen, mostly proteins and amino acids, the engine of plant growth.
But when you turn up the heat, the nitrogen actively tries to escape. And it happens in this very predictable, temperature-dependent cascade.
A cascade? What do you mean?
Well, when the internal temperature hits around, say, 200 to 300 degrees Celsius, the weakest bonds in those proteins just break apart. The nitrogen pairs up with hydrogen and starts escaping up the chimney as ammonia gas.
Oh, wow. Which explains why raw manure smells the way it does, but just accelerated by the heat.
Exactly. But as you push the dial past 400 degrees Celsius, those intermediate compounds crack open even further, and a significant portion of the nitrogen actually releases as hydrogen cyanide.
Wait, hydrogen cyanide? Like the highly toxic gas?
Yes, exactly. It's a highly toxic gas pathway that peaks right in those intermediate temperatures. And by the time you hit 600 degrees, which is a very common target for creating that really premium biochar, you are losing nitrogen purely as N2 gas.
It's going right up in smoke.
Literally. I mean, studies show a staggering drop-off. At a gentle 300-degree bake, you might retain about 82% of your starting nitrogen. But if you crank the heat to 1100 degrees, your retention plummets to 10% or less.
Okay, wait, let me push back on this for a second. Because if I go to the store and I look at a lab analysis printed on the back of a bag of manure-derived biochar, it might still say it has like 2% to 5% total nitrogen.
Yeah, it will.
So doesn't that mean it's still a good fertilizer? I mean, is this like having $1 million locked in a titanium bolt, but you just don't have the combination?
That is exactly what it is. The nitrogen that does survive that intense heat, the stuff the lab equipment is detecting, it doesn't stay in an accessible form.
So what happens to it?
It undergoes a process where the nitrogen atoms physically replace carbon atoms. They get woven into the actual aromatic carbon rings of the biochar itself.
Oh, weird. So it becomes part of the structure.
Right. They form these heterocyclic compounds, specifically pyrrolic N and pyridinic N. Agronomists call this black nitrogen.
Black nitrogen, that sounds vaguely ominous.
Well, it's highly stable, and for all practical purposes, it is practically invisible to plant roots. It's completely locked away.
Okay, so if the nitrogen is locked away in the vault, then applying fresh biochar to soil must be, like, completely useless, right?
Oh, it's actually worse than useless. In the short term, it can be actively harmful.
Wait, harmful? Because it's an empty carbon skeleton?
Exactly. It triggers a phenomenon called nitrogen immobilization. See, fresh biochar is incredibly carbon-rich but nitrogen-poor. The C to N ratio is massive. When you put it in soil, the native microbes wake up and they just go into a feeding frenzy on all that carbon.
And microbes need nitrogen to build their own cells, right?
Right, so to build their own DNA and cell walls, these microbes scavenge all the available loose nitrogen that was already in your soil. They actively outcompete the plant roots, causing acute nitrogen deficiency in your crops.
Ah, that's why the tomatoes turned yellow. The biochar didn't poison the plants, it mobilized an invisible army of microbes that starved them.
You hit the nail on the head.
So how do we fix this? We can't just throw the bag away. How do we make it safe?
We have to charge the sponge, or dope it, as some call it. Because biochar is highly porous, right? It has a very high cation exchange capacity, or CEC.
Which means it has an electromagnetic charge that grabs onto nutrients.
Exactly. It acts as a permanent sponge. So by co-composting it, or soaking it in liquid manure, or even exposing it to captured ammonia gas before it ever touches the soil, you fill those microscopic pores with bioavailable nitrogen.
Okay, that makes total sense. So we've covered nitrogen, it turns into gas, escapes up the chimney, or becomes this locked up black nitrogen. What about the heavy stuff? What happens to phosphorus?
Phosphorus is a totally different story. It is unique because it does not vaporize at normal biochar temperatures. Its boiling point is over 2,700 degrees Celsius.
Oh, wow. So 600 degrees is nothing to it.
Nothing. So as the carbon and oxygen and hydrogen burn off, the absolute volume of phosphorus stays the same, but the overall mass shrinks, meaning it effectively concentrates.
So it's left behind in the ash.
Right. The studies show an enrichment factor of about 1.3 to 4.3 times the original amount of phosphorus.
Okay, here's where it gets really interesting to me. If the phosphorus is concentrated by that much, logic suggests this should be the ultimate hyper-concentrated fertilizer. So what's the catch?
There is a major catch. Just like nitrogen changes shape, phosphorus changes its physical state. It's a crystallization trap.
Crystallization.
Yeah. At lower temperatures, say 300 to 400 degrees, the organic phosphorus-like phytate in crop residues breaks down into these moderately available polyphosphates. Plants can use that.
Okay, so a low temp bake is fine for fertilizer.
But as heat increases past 500 degrees, the phosphorus reacts with the calcium and magnesium that's left in the ash. The atoms actually fuse together, forming these incredibly hard, insoluble crystals.
You mean it literally turns into a rock?
A very specific rock, a mineral called hydroxyapatite.
Hydroxyapatite. Wait, isn't that the exact same mineral that makes up human tooth enamel?
It is literally the exact same thing, biological stone. So the total phosphorus on your lab report might look huge, but the bioavailable phosphorus drops to less than 1 to 10%.
So you're basically planting crushed tooth enamel in your garden and expecting the tomatoes to eat it.
It's crazy, right? Researchers actually proved this in pot experiments recently. They took biological waste and baked one batch at 400 degrees. That low-temp biochar could replace about 66% of a synthetic fertilizer.
Because it hadn't crystallized yet.
Right, but when they baked that exact same raw material at 600 degrees, its fertilizer value plummeted to just 6 to 9%.
Wow, from 66% down to single digits.
The heat locked it inside a crystalline fortress.
So temperature really is the master dial here, controlling everything. So what does this all mean for us? Should we just bake everything at a low temperature and call it a day?
Well, that's the ultimate trade-off of the whole biochar industry. If you use low temperatures, like 300 to 400 degrees, yes, you save the nutrients, but you create a weaker, much less stable carbon structure.
So it might just break down in the soil in a few years and you lose the carbon sequestration benefit.
Exactly, but high temperatures, 600 degrees, and up create this incredible permanent carbon sequestration. It makes a great porous sponge that holds water forever, but it utterly destroys the immediate fertilizer value. You really have to pick your priority based on your feedstock and your long-term goals.
Okay, but if I'm holding a batch of that high-temp 600-degree biochar with all this crystallized hydroxyapatite, is that phosphorus just trapped in the vault forever? Because, frankly, we're running out of mineable rock phosphate globally.
No, it's not lost forever. You just need to unlock the vault. And we have biological and environmental allies to do that.
Allies? Like what?
Well, environmentally, applying it to highly acidic soils helps. The natural acid slowly dissolves the crystals over time. But even better, you can deploy phosphate solubilizing bacteria, or PSB, alongside the biochar, Or mycorrhizal fungi.
Oh, I love mycorrhizal fungi. They make those massive microscopic webs
Yeah.
underground, right? Trading with the plant roots.
Exactly. And when you deploy them with biochar, these fungi actually secrete organic acids. They actively mine the phosphorus right out of the biochar pores and deliver it to the plants over years or even decades.
That is incredible. So it becomes this secure, slow-release bank account rather than just fast cash fertilizer that washes away in the rain?
Right. And understanding this chemistry is the key to sustainable agriculture and the circular economy. We can recover these nutrients from sewage and manure so they don't pollute our rivers and safely store them in the soil for future generations.
That is such a vital point. So to summarize for everyone listening, we really need a mindset shift here. Biochar is not a direct replacement for Miracle-Gro. The intense heat of pyrolysis either sends nitrogen up in smoke or locks it into black nitrogen while crystallizing phosphorus into literally insoluble tooth enamels.
Yeah, you have to stop seeing it as a fertilizer.
Right, we have to view it as an incredibly powerful sponge and a slow-release soil conditioner. It's all about how you prep it.
Absolutely.
You know, all this leaves me with a final kind of provocative thought to chew on.
Well, let's hear it.
If raw biochar is basically this empty, high-tech mineral skeleton, something that actively needs microbes and nutrients preloaded into it to function, maybe we shouldn't think of it as an agricultural product at all.
What do you mean?
Well, what if we viewed raw biochar the way a marine biologist views an empty coral reef, like those concrete structures they drop into the ocean?
Oh, right, the artificial reefs.
Exactly. When it hits the seafloor, it is entirely lifeless. It's a blank artificial habitat. It only works if we deliberately seed it, train it, and populate it with the exact microbial ecosystem our specific soil needs.
Wow, that is a brilliant way to frame it. You're just buying the architecture.
Right. You still have to build the city. Just something for you to think about the next time you're standing in the garden center holding a bag of black dirt. Thanks for joining us on this deep dive, and we'll catch you next time.